Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 44 of our induction motors chapter, right? So we will be discussing about dynamic behavior of any motor and also the testing of induction motor. What are the different tests that are performed on induction motors? First thing is what do we mean by dynamic behavior? Okay. So dynamic behavior basically means if I have a motor and I have a shaft and suddenly I connect a load, right? I connected load with the shaft. I have connected a load. So load basically can be anything, right? Load can be anything. It can be a pump, like the fan also, it is also rotating, right? It has some load associated, that those wings are its load, right? Rotor is just a small portion. So if I am able to show you, will I be able to show you the fan? You know the fan, right? So the fan has, like, this is a fan, and the fan, okay, very bad drawing. The fan basically has three wings kind of thing, right? So the rotor resides here actually, and these wings are its load. Okay, so what happens when load is connected suddenly, right? So this we have already discussed, that the developed power, or assumption is we are assuming that both of them are equal. Developed power is equal to shaft power, which is equal to torque, right? And load itself will provide some load torque that will be in the opposite direction. So in steady state, the net, what will be the net torque? Net torque will be T minus TL. In steady state, what will happen? This is equals to basically J into alpha, where J is the moment of inertia, right? J is the moment of inertia, and this d square theta upon dt is the angular acceleration. So this is known as J alpha, where alpha is the angular acceleration, right? And this is just a moment of inertia. Not moment of inertia. I have also forgotten what is this J. This J is something, right? I have also forgotten. This J is something. Okay, I don't remember exactly the this name of this. Okay, so it is analogous. Okay, sorry, it is moment of inertia only. It is moment of inertia. What I am talking. It is moment of inertia only. Okay, so here what I can say is, in steady state what will happen? In steady state, the this load will rotate with a fixed speed. So the angular velocity will be fixed, constant in steady state. At steady state, the angular velocity will be constant. So if angular velocity is constant, basically, right, this we have discussed previously as well, that what is this d square theta upon dt square? This also can be written as J into d omega by dt, right? So if omega is constant, that means what? D omega by dt is 0. Sorry, yeah. So hence this net torque will be 0. That means at steady state, the developed torque will be equals to the load torque. Okay, this is what we know. Now few cases are there, right? So initially, if I just start the machine, initially what will happen? The If I have just started the machine, let's say the load is not connected, so TL is less than developed torque. Then what will happen? Then the net torque is positive. If the net torque is positive, that means what? That basically means there are three cases, right? We have discussed this previously in DC machines. We have discussed this. So if the load torque is less than the developed torque, then the net torque is positive. This is the case one. If net torque is positive, that basically means that d omega by dt is greater than 0. That basically means that omega will increase. Omega will increase. Okay, so now if the torque is less than developed torque is less than the load torque, that means what? That means the net torque is negative. If the net torque is negative, that means the d omega by dt is negative. If d omega by dt is negative, that basically means that my omega will reduce. Okay. And in the case 3, if the developed torque is equals to TL, that means the net torque is 0. That means basically omega will be constant. That is d omega by dt is 0. That means omega is constant. Okay. So yeah, basically there will not be any acceleration, neither deceleration, right? So these are the 3 cases. Now I want to discuss about stability. Okay, real quick, I want to discuss about stability, right? So I'm giving you options. These 3 are the options. Out of these 3 systems, can you tell me, can you identify which system are stable, which are inherently stable? So slowly we will see what does stability mean. So stability, I will describe what does stability mean. Stability refers to the system's ability to return to its original or equilibrium operating condition after a small disturbance have been applied. A system is said to be stable if after a disturbance it tends to return to its original state or operating point. So if I see for this ball, right, if I tend to disturb this ball, if I, let's say, if I am giving it some force in the right hand side direction, what will happen? This will go here, then due to gravity, this will again come back here, right? This will like move like this. This will go here, then it will come back, then again it will somewhat go there, come back, go there. It will oscillate, 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 and ultimately it will be stable here. What about this point? If I provide a very small disturbance, what will happen? If I provide even very small disturbance, this will start from here and this will totally come down, right? So basically it is not reaching to its previous state. Here also, if I provide a very small disturbance, what will happen? Will it return to its original path? No. This is not inherently stable. This system is not inherently stable, right? Why? Because if I disturb it, right, and if I assume that there is no friction, what will happen? This will move with a constant speed. So I give a small disturbance to this. So basically, do I have anything? I don't have any ball. So basically, if you see, this is the object, right? And if I give this a small disturbance, what will happen? This will move forward. If I give a small disturbance, this is moving forward, right? But here I have friction. So it stops. But assumption is here there is no friction. And one more thing, stability means it should return back to its previous position. So will this ever return back to its previous position? Let's say it was here in my hand. If I just give it some disturbance, it moves in the front, right? Okay, it comes back here, but it does not actually in real life. So if I give it some push, right? If I give it some disturbance, it moves forward. It will never come back in this position. So it is not stable. So only the first system is inherently stable. Now, how can I mathematically explain this? How is it like, how can I mathematically explain this that it will be inherently stable? Okay, so here, like this, right, this should be actually not here, this should be here, this should be here. Okay, this is not, we don't have any space over here. Okay. I don't have space, we don't have space. Where do I place it? Let me place it here only. Okay, no option, no other option. Okay, so how can I identify from the graph itself whether it is stable or not stable? So one thing you should observe, let's say I am at this is my load torque, right? So load torque is operating, like it can cut the graph, the torque speed graph, 2 points. So basically I know that omega will be constant, right, when the load torque is equals to the net torque. Okay, sorry, this should be here only. So when the load torque is equals to the developed torque, not the net torque, when the load torque is equals to the developed torque. So this graph is of the developed torque. Okay, so what can I say is that there are 2 cases for which I can get a constant speed, because ultimately the net torque has to be 0. So wherever the load torque and the developed torque is equal, that will be my steady state. That is known as the steady state, right? So the graph, like my motor can stop here at this point and at this speed. But can you tell me which out of this, which one is the stable speed? which one is the stable speed. So here, right, what will happen, let's say I choose a point, let's say my motor is stable at point A, so case A, right, case A. If I assume that the motor will be stable at point A, so if I give some small disturbance, let's say I give this a small disturbance, I will copy this graph. Let me not actually do anything with the graph. Let me delete this thing. If I see over here that if I see over here that this is my Ni basically. So what I can say is, if I give it this is small disturbance, let's say I'm at point A, I give my motor a small disturbance, I reach my point B. For some reason the developed torque reaches point B. So what will happen? What will happen basically? So if I change my developed torque slightly, I'm giving a small disturbance. So what is the net torque now? T net dash, it is basically always T minus TL, and this time I have just given it a small disturbance that is above TL, right? So T is greater than TL, so what is happening? So the net torque is positive. If net torque is positive, that means what? That basically means there is acceleration, so it will accelerate further. So there is acceleration. If there is acceleration, that means what? That basically means speed increases. Speed increases. So what can I conclude from this? The conclusion is that if I give it a small disturbance on the right hand side, that further increases the speed even more. So if I give it a small disturbance, what will happen? That will further increase the speed even more. So basically the developed torque will keep on increasing. The developed torque will keep on increasing further. Okay. Let's take for the other case, let's say I had given it a disturbance in the other point here. Okay, if I give it a disturbance here, what will happen? Here my T net dash, basically T net double dash is equals to T minus TL. Okay, so T minus TL, T minus TL, so T minus TL, so it is basically negative, right? T minus TL is negative because this time T is lower than the load torque. So what will happen? Net torque is negative, so there is deceleration. There is deceleration. If there is deceleration, that means what? That means speed will reduce further. Reduces. So basically this graph will, like, speed reduces, that means I will go on the left hand side, so it will go more further down. So this point is totally not stable. So what can I conclude? I can conclude that a point is unstable equilibrium. So it is unstable, right? A point is totally unstable because, like, same thing, if I give some disturbance, if I increase the speed slightly, what will happen? The rotor speed will keep on increasing. If I decrease the speed slightly, the rotor speed will keep on decreasing. Hence the point A is unstable. What about point B? So for the point B, I will directly do here. So for point B, if I see, let's say I am giving it a small disturbance, I'm increasing the speed slightly. If I increase the speed slightly, what will happen? If I increase the speed slightly, then I observe what is the net torque. Net torque dash T net dash is basically T minus TL, right? But this time, if I observe that the T is lower than TL, T is lower than TL, so this will be actually negative. If this is negative, that means what? That means I will observe a deceleration. Acceleration. Okay, and so uh, so basically there will be deceleration. That means the speed reduces. Speed reduces. So if I try to increase the speed, because I have given it some disturbance, the speed reduces. So it will go back to this point, stable point, right? It will go back to this point. Same case will happen here as well. If I try to reduce the speed, if I reduce the speed, so my T net dash dash again will be T minus TL. But this time, if I have reduced the speed, but my T graph, the developed torque is higher. So this is the developed torque, right? This is the graph of the developed torque. So developed torque is higher. So this will be positive. So there will be acceleration. If there is acceleration, that means, what can I say? I can say that the speed increases, right? So if speed increases, basically what will happen? So it will again shift rightwards, right? It will again shift rightwards. So speed will increase. So again it will come back to this stable point. So B point is a stable equilibrium. So same thing, whatever I have explained is same thing is written over here. Okay. So but mathematically, what is the understanding? Mathematically, the understanding is that here if you observe, right? Here if you observe the dt, the slope of the graph, right? Dt upon dn, right? It was actually positive in this point. But here if you observe in the point, this is the point A, at A, and if you observe dt upon dn at point B, it was negative. So basically what I can bifurcate here is that this region is actually the region of instability, because here the dt upon dn is always negative. So this is the unstable region. Unstable region. And this particular region is a stable region. Why stable region? Sorry, here it is always positive, sorry, not negative. Here it is always positive. Stable region in which dt upon dn is negative. Okay. So same thing is written like n or omega, both are proportional to each other. So stable points will lie where the slope is negative with respect to the torque, and unstable points will lie where the slope is positive with respect to the torque. So this principle forms the basis of stability analysis in electrical drives. Okay. So this is a very basic point. So some question came in gate itself, right? So this question came in gate. So the torque speed characteristics of motor with respect to the load torque in two cases are shown. The stable operating points are, okay, here, right? What is the stable operating point? Here if I see, like, either you can use the formula or you can go with basics, whichever one is suitable to you. Here if I observe, right, like this is already, we have solved this. So if I increase the torque at this point slightly, right, so the speed has also increased, right? So but what is the net torque? Net torque has also increased, it is positive, so it will further keep on increasing. So P is definitely not a stable point. Okay, right? That is what they are asking. Okay, sorry. Okay, please keep this in mind. This is the direction of the speed. This is the direction of the speed, right? Keep this in mind. This is the direction of the speed. It is not like if I'm moving in this direction, right? Speed is actually reducing. So if I'm moving here, the speed reduces. So here the speed reduces, right? Why speed reduces? Because if you observe, this is the direction at which the speed is increasing, right? So if I'm moving in downward direction, that means the speed reduces. Okay, they have given the graph intentionally very bad so that you make a mistake, as I was making the mistake, right? So here, right, again, net torque actually increases, right? It's positive. If it is positive, what will happen? Speed is reducing, but there is acceleration, right? If acceleration, speed will increase. So basically what happens, I made a disturbance, I reduce the speed, but due to the feedback, speed is increasing. So again it will come back to the stable point. Okay, so P point will be a stable, definitely P point is a stable. Same thing, you can apply the same principle. Q will not be stable, P will be stable. Okay, same thing here. Again they have flipped the torque and speed graph, right, intentionally, so that you make a mistake. Okay, so here again if I observe that if I increase the speed here, right? So this is the okay, this is the motor torque and this is the load torque. Okay, so if I'm here in this position, so the speed has increased. Let's say this was the R position, so I move from this position to this position, so here the speed has increased, right? Speed increases. If speed increases, what is happening to the torque? So here the torque was equal. Here I observe that load torque is higher. Sorry, is the load torque really higher? No. Here I am here. Okay, load. Okay, this is the developed torque. Okay, and in this developed torque, what is the, okay, the load torque? Okay, uh, okay. If I slightly give it a disturbance, okay, I'm at this position. Load torque here was constant. Here actually it is varying. So how do I identify what will happen? Okay, so seems like load torque is same. Load torque is almost same. It is same, right? Okay, am I doing it correctly? If I increase the speed slightly, okay, if I'm increasing the speed slightly, what is happening? The load torque will, okay, if I increase the speed slightly, right? Let's say I'm increasing the speed from here to here. Okay, from R to this point, what is happening? Then I'm increasing the speed here. So basically this is the speed. Okay, sorry, that is what I was making mistake. So I am at point R and I am increasing, let's say this is the speed, right? Initial speed at R. So I'm here, I'm making a small disturbance. I'm increasing the speed to nr dash. Okay, so I'm here. So in this particular case, what is the this is the developed torque and this is the load torque, right? So I observe the developed torque is higher than the load torque. If I see, the developed torque is higher than the load torque, like developed torque is here and load torque is here, right? So of course the developed torque will have higher magnitude, higher value. So the net torque is positive. So basically it is accelerating, right? Accelerating, alpha is greater than 0, so there is acceleration. So speed further increases, so nr dash will keep on increasing. So it is unstable point, right? It will just blast out, it will go outside. So it will basically reach this point. This point is a stable point. Okay, you can do the same thing. So let's say I'm here, okay, and I'm increasing, this is my speed ns, I'm increasing the speed to ns dash. Okay, or let's say I'm decreasing, right? Because increasing is there, so I will decrease. If I decrease the speed to ns dash, if I decrease the speed to ns dash, what will happen? So if I observe, this is the torque here, right? Again the load torque, and this is the developed torque, right? Again I see that the load torque is, developed torque is greater than load torque, so there will be acceleration. If there is acceleration, speed will increase. Speed will increase. So I see I am reducing the speed from n to n dash, but speed is increasing. So it is again going back to s point only. So I can say that p and s point will be the stable point. So p and s will be the stable point. That is the option B. So that's why you should not just mug up the formulas. You can do it with that formula, right? dt upon dn, you can do it, no problem. But fundamentally you should also be very clear how that formula came. Okay, how that relation came because gate, what will gate do? Gate will basically do something like this. They will flip the graph, they will make it very difficult to understand, okay, to find out that slope. It is, they will not give you this simple graph. No, they will of course not give you this simple graph, right? They will give a graph like this only. So that's why I'm teaching you for the worst possible case. Okay, I'm not teaching you easy things here, because you will be very happy if I teach you easy things, but when you will go to the exam hall, trust me, you will feel like you are in hell. So let's now discuss about testing of three-phase transformers. So it is almost similar as, sorry, not transformer, testing of three-phase induction motor. It is almost similar as transformers. So the testing of induction motor and transformers go hand in hand. So if you remember, what kind of tests we had in transformers? We had a open circuit test, and we have a short circuit test. Okay, so in open circuit test, basically what do? We operate in no load. So here in induction motor it will be called as no load test. No load meaning there is no load connected. Basically in the rotor side there is no load, it is open. So basically when your fan, right, or your motor, whatever motor that is driving, right, there is no load. Basically if you have a bike and that bike does not have any passengers, okay, it is just running by on its own, so that means what, it is in no load, it has no load on it, right? So no humans are seated on it, so it is no load. Same here, there will be no load connected. So during no load there will be few losses. Those losses will measure with the help of wattmeters, ammeters and voltmeters, right, currents, voltages and powers. So we will discuss about that. And in short circuit test, what was a short circuit test? When the transformer, the rated current was flowing through the transformer. The short circuit test was when rated current was flowing through the transformer. It is same as blocked rotor test, right? Like it will be called in induction motor a blocked rotor test. What we will do, we'll try to flow the maximum amount of current. When the maximum amount of current will flow, when there is maximum amount of flux linkage or flux change. When can the maximum amount of d phi dt be possible? If I somehow make the rotor stationary. If I make the rotor stationary, then the rotating magnetic field is rotating with speed ns and there is huge amount of flux cut, right? Huge amount of relative speed between the rotor and the rotating magnetic field that will produce the maximum amount of current. So due to that, it is called as block rotor. We basically block the rotor. We do not let the rotor to move. Okay, we do not let the rotor to move. That's it. Okay. So yeah, that was the thing over here. Now one key point is, I hope you understand. If you know this circuit diagram, it's very good. If you don't know, then it's totally fine. So we have two wattmeters, W1 and W2. So you might think that in case of three-phase system, I have three phases, so I might need 3 wattmeters. But you will study from me in measurements that we will actually not need 2 wattmeters. We will not need 3 wattmeters to measure the power through 3-phase. We will only need 2 wattmeters. So if we need only 2 wattmeters, special connections are there which will be very helpful. Even though if the system is unbalanced, then also we can measure the power with 2 wattmeter method. Okay, this you will study in measurements. So these are the connection diagram: 2 wattmeters and ammeter and voltmeter. One thing, if you notice, that we have not connected anything to the rotor. Everything is connected to the stator. Okay, why is it connected to the stator? So because of course there is no electrical connection in the rotor side. For, if you remember, for slip ring induction motor, there were few connections, right, at the output, but that is too hectic, right? We don't want those kind of like rotating parts near our electrical connections. So whatever electrical connections we will do, we'll connect it on the stator side. So all electrical equipments will be connected to the stator side. They will not be connected to the rotor side. They will be connected to the stator side only. Okay. So yeah, that is the case over here. So these are the few prerequisites. So let's discuss about the no load test. So as I have already told you that we will have two kinds of tests: no load test and block rotor test, which are similar to transformers. So in no load basically means the slip, right? Slip will be almost zero. Why the slip will be almost zero? So if you have noticed one thing, so whenever you have a motor or a fan, right? You have a fan. So you have this fan, correct? You have this fan. Okay, so in the fan, if you remember, if it's a new fan, right, with the same regulator point, let's say regulator point 2, right, at the speed rating of 2, the fan rotates quite fast, right? After 1-2 years, right, 2 years, what happens? In the same regulator knob, okay, same regulator position 2, will the fan rotate with the same speed? No, because the fan has collected dust, right? It will be bit slower because it will have some wear and tear. There will be a bit of friction in the mechanical parts. Due to all those things, the fan quality has degraded. Due to that, the speed has reduced. So basically what does it mean? It means in no load, when there were no dust and stuff, right, the fan was rotating very fast. So if the fan was rotating very fast, rotor speed was very high. So in no load, what will happen? We had already discussed this previously as well, that the rotor speed will be almost equal to the synchronous speed. Almost, it will almost try to follow the rotating magnetic field. So rotor speed will be almost equal to the synchronous speed. Okay, so that is the case over here. Now, yeah, I hope you have understood this point. Now, yeah, now let's discuss about the block rotor test. In block rotor, what did I tell you? We will block the rotor. If I am blocking the rotor, that means what? That means basically the rotor does not move. That means NR is 0. If NR is 0, that means what? Slip will be what? Slip is NS minus NR divided by NS. So slip will be 1. Okay. In addition, the retardation test is used for separating losses. Okay. So in transformers, we do not have any rotating parts, right? So there is one additional losses known as the rotational losses. How will I measure that? Rotational losses. So for that, we will have a separate test known as retardation test. Okay, how do we measure it? All those things I will explain. Trust me, no one will explain you these things, right? These external things. How do we measure the power in the retardation test? And one day, GIT examiner will ask questions, and you guys only will be able to solve it. Okay, so it is also called sometimes as locked, sometimes blocked or locked rotor test. Okay, it is also called as the locked rotor test. Okay, so yeah, these are the things basically. So like this is the equivalent circuit, right? So once you see at no load, basically no load means what? S will be tending to 0. If S tends to 0, this is infinity. So it is almost like a transformer, right? So this will tends to, like the resistance, this is what? This is a electrical equivalent of the mechanical load, right? Electrical equivalent of the mechanical load. So here this will be, if S is tending to 0, this is 1 or almost equals to 1 by 0 minus 1. So this will be tending towards infinity, right? So the resistance is very high. It basically means that the current through here will be very low. Okay, very low, almost 0 amperes of current. Correct, almost 0 amperes of current. So most of the current will flow through this, right? But still there will be some current flow, because rotor will still rotate, right? Rotor will still rotate. Correct, that is again true. Rotor will rotate. So if rotor rotates, and if the rotor is rotating, there will be some rotational losses. Those are fixed losses, as we have discussed in DC machines. So there will be still, even though current is almost 0, not exactly equal to 0, some small amount of current will flow, because if you remember, in no load the current is still very good amount, right? 30 to 40%, right? So there will be still rotational losses, because rotor is still rotating. Okay, rotor is still rotating, there will be still rotational losses. So now what I can say is that yeah, these are the things basically. So what we can do is, we can neglect this one, right? We can neglect the copper loss here, right? Because here on this side current will be still almost negligible on the rotor side, because current will flow but very low amount of current will flow. Remember, this is the rotor side. So all this whatever I have written is referred to the stator side, but rotor copper loss will be very low. But one thing we know, that in induction machine, right, the air gap is larger. If the air gap is larger, the magnetizing current is larger. We had already discussed. So magnetizing current or no load current is almost 30 to 40%. So here this current will be still large, right? This current will be still large. If this current is large, then this copper loss will be large, right? This copper loss will be large. That is, stator copper loss will be large. So in case of transformers, if you remember, we ignore the stator copper loss. In case of transformers, we ignore the stator copper loss, right? Because the current, no load current was very low. right? But this time I cannot neglect the stator copper loss. It will be high because it has to supply the magnetizing current, and magnetizing current itself is very high. So here the stator copper loss will be very high. Okay, so that is the thing, stator copper loss will be very high. We will have losses here, so I cannot neglect the stator copper loss. Okay, I can neglect the rotor copper loss. So remember what kind of losses I am measuring. So this wattmeter and voltmeter and all those things, right? What will it measure? So the ammeter, this time ammeter current will be the no load current, that is fine. Ammeter will almost approximately measure the no load current, approximately almost it will be equals to the magnetizing component, right? Mainly contributed by the magnetizing component. Now what will the voltmeter measure? Voltmeter will, like, we will apply obviously the rated voltage. So rated voltage we will apply. So V will be the rated voltage, whatever V rated we have, to get the rated flux. Because what is my flux? Because I need the rated magnetizing current. To get the rated magnetizing current, I need the rated flux, that is phi will be proportional to V by F, right? Phi will be proportional to V by F. So if phi is proportional to V by F, that means what can I say? I can say that I have to provide, obviously frequency is constant, I have to provide rated voltage, right? If I provide rated voltage, I'll get rated flux. So I have to provide rated voltage. What will the wattmeter measure? I told you, right? Wattmeter will measure the overall power consumed in the circuit, right? In the three-phase circuit. So wattmeter this time will measure the stator copper loss first of all, because the no load current is higher. So stator copper loss, plus it will measure the, of course there will be iron losses here in the core, iron loss. And remember, if your motor is rotating, there will be rotational losses, as I have told you, right? So there will be rotational losses. That's why that's why we have this other test known as retardation test. Okay, retardation test. So yeah, this is basically the no load losses. We have constant loss, iron loss, plus friction and windage. Windage loss is the rotational one loss, right? As we have discussed here. So main purpose is to determine the constant losses. These are the constant losses. Okay, and why I cannot ignore the windage and this friction and windage plus the stator copper loss? Why cannot cannot ignore the stator copper loss? Because why? Because my magnetizing current IM will be 30 to 40% of 30 to 40% of rated current. Okay, so that thing you have to do. Now so it find out this constant loss, plus there is bit of, because copper loss is a variable component of loss, but as I am applying rated voltage, right, only the no load current will go, that is almost constant, so that also I can assume to be constant. Okay, but although copper loss is in itself variable because it depends on the load current, but my load is open, right, there is no load, so that's why this also is included in the constant losses only. So with this we will be able to find out the shunt parameters XM and RC. How will I find out the XM and RC? So what we can do, I know the voltage, right? I know the voltage, I know the current. So voltage by current will give me what? So this is almost negligible current, right, this side. So here huge current is flowing. So I will have this R1 JX1 will be there, and this RI JXI XM will be there, right? But I can roughly approximate it. So somehow if I am able to measure the voltage in this side, that will be great for me. So basically, right, what I can say is V by I will be a combination of okay, where is the other side? Okay, that I will discuss in the next slide. I will discuss how will I measure the shunt parameters in the next slide. Don't worry, I will come to this. How will I find out this shunt parameters in the next slide? So what is the procedure? Run the motor without any mechanical load on the shaft. So on the shaft there should not be any load. Okay, that is the first thing. On the shaft there should not be any load. And next, a balanced three-phase supply at rated voltage and frequency is applied to the stator. Okay, So a balanced three-phase supply will be applied to the stator side with rated voltage. Since the shaft is unloaded, the motor draws small no-load current, not small though, it will not be small actually, it will be considerable amount. Okay, motor will draw some no-load current, just enough to produce the rotating magnetic field IM and to overcome the core and friction losses. So basically the wattmeter, the no-load losses will measure what, as I have discussed, it will measure the iron losses, it will measure the stator copper loss, it will measure the friction and windage loss. Okay, it will measure the friction and windage loss. Now what will be the stator copper loss? Stator copper loss will be what, I know the current through the ammeter, right? It will be 3 into I naught square into R1, because it's a three-phase system, it will be 3 I naught square into R1. Okay, so I hope you have understood that point. So okay, iron loss is voltage dependent, that's why obviously, as I have discussed, we will conduct the test in rated voltage. Copper loss in the stator is very small, it will not be neglected. Say rotor copper loss will be neglected, but stator copper loss will not be neglected, as the rotor current is nearly zero, as the slip is very small, because the resistance will be very high, the equivalent resistance here, right, will be very high. Now what will be the this impedance? So as I was discussing, how will I measure the impedance of the how will I measure the shunt parameters Ri and Xm, right? So what we can say is, this is Z1, let's say this is Z1 and this is Z2, right? And one thing we know, that generally the winding resistance and all those things are very smaller compared to the core magnetizing component resistance and reactance, right? So I can say generally the magnitude of Z1 is very less than Z2, magnitude of Z2. So basically what I can say is, then I can roughly, if I am applying a voltage V over here, I can roughly bring that voltage over here. V dash. Okay, I can roughly bring that voltage V dash. So V dash we can say is equals to magnitude of like Z2 divided by Z1 plus Z2, and as I have already told you, right, Z2 is very larger, so into V, input V, so it will be roughly equals to V only, because Z2 is very large, right? So if this is very larger, then Z1 plus Z2 is roughly Z2 only, so it is V only. So basically what I am coming to the conclusion is that V upon I, right, the ammeter current and the voltmeter will yield me roughly, it will be equals to Zi. So from here I will be able to get the impedance of the core component, right? So now what about the this individual component shunt parameters Xm and Ri? So how will I find out the Xm and Ri? So to find out the Xm and Ri, what I can do is, if I somehow am able to, so this is PO, right? This is PO. PO is a different value. PO is what? PO is basically constant loss, iron plus mechanical plus the stator copper loss. Don't forget the stator copper loss. This will also be there. Stator copper loss. Okay. This is equals to my PO, right? But if I am somehow able to from this extract the iron loss, I will tell you the method how will I extract the iron loss. Iron loss is a separate thing, right? Iron loss is a different thing. From the iron loss, what is iron loss? Iron loss would be, three-phase iron loss would be root 3 into V into the ammeter current IO into the cos phi O, basically the power factor angle of this particular impedance Z2, right? So from here I can directly find out what is my cos phi O. Cos phi O will be Pi divided by root 3 V into IO. Okay. So this is what my cos phi O is. So basically from here you can easily find out what will be the other values. So if I want to find out what will be the shunt parameters. So in case of a series connection, we write uh, z equals to x plus j, sorry, r plus jx. Now it's a shunt, so I will find out the ratio of I upon v, right? So I upon b will roughly be equals to the admittance of the core component yi, that will be the conductance gi minus the susceptance bi. Okay, so what is my gi? So gi, I know the power factor angle, all those things, right? So gi will be basically the admittance yi cos phi naught. If you are having difficulties in understanding this, that means you have to go and watch the the phasor chapter. Okay, there we have understood everything. So basically this is my real component where my conductance will be lying. This is my component where my susceptance would be lying, bi, right? And this will be the equivalent yi, the admittance, and this will be the angle basically from the uh, real component phi naught, right? So yi cos phi will be yield me the conductance, and the susceptance will be yi sin phi naught. Okay, so this will be the susceptance basically. So this is how you will find out the shunt parameters, but still the doubt is there that how will I, sir, how will I find out this pi? So we will discuss about this in the next test. That is what? That is the retardation test, or also known as the deceleration test. So if you remember, again I will take the fan example, that I have a fan here, right? I have a fan here. Very bad drawing of fan. And one thing is that if I have turned off the fan, does it instantly come to stop? Fan does not stop instantly after switching it off. Okay, it does not stop instantly after switching it off, right? Why it does not stop instantly? Because fan will have its own inertia. Fan will have its own inertia, so it does not stop instantly. It comes to stop, but after a while. So from there, actually, I will be able to find out what is the rotational losses, because it's kind of constant. We'll assume it to be constant almost, so we can find it out. So what is the purpose of this retardation test? To separate the iron losses from the rotational mechanical losses, like friction and windage. Okay, so the motor will be driven up to the rated speed, and of course with no load connected. Then the supply will be disconnected, just like switching off your fan. So as soon as you will switch off your fan, the rate at which the motor slows down is monitored. Why? Basically, I will plot the speed with respect to time. So if I am plotting the speed with respect to time, and if I am able to get the slope of this graph, so I will plot the speed with respect to time. Okay, now if I am able to get the slope of this graph, so basically speed is what, this is like revolutions per minute or something, so this will be proportional to the radian per second, right? Omega. So what is the slope? Slope will be what? D omega upon dt. What is d omega upon dt? It is simply alpha, the angular acceleration. And one thing we have already discussed, if you remember, force is equals to what? Force is equals to mass into acceleration, linear acceleration. So in rotational components, what is torque? Torque will be equals to J alpha. Okay, what is J? We have already discussed this previously as well. J is just like a mass, right? It is moment of inertia. Moment of inertia. It is an angular component thing. So it is moment of inertia. Okay, so basically it is basically a function. So j is a constant number. J is a constant number. J will be constant only. Alpha will be a function of omega, speed, right? And if I assume that, like, if I am able to find out the energy loss, basically I have to find out the overall energy loss. So what will be the power? Power. If you remember, what used to be the power in case of this? So if you remember, the work done was what? Work done du was F dot ds, right? Small displacement. So overall work done will be, this will be F dw by d. Okay, if I integrate this, it will be integration of dw, it will be w F dot ds. This will be the overall work done, correct? Now okay, because this is with respect to time, if I divide this, okay, this is the overall work done, right? So now what I can do, I can differentiate with respect to time. So dw upon dt will be equals to what? Force into ds upon dt. Now what is ds upon dt? So ds upon dt is basically what? Ds upon dt is velocity, right? Velocity. So ds upon dt will be velocity. So what is dw upon dt? dw is rate of work per second. So it is power. Power will be force into velocity, F dot b. Same thing we will do here as well. So I will be able to find out the power, right? Power will be force into here it will be not be force, it will be torque into omega. Omega, and torque itself is a function of omega, right? So remember, it is a function of omega which is always varying, right? So I have to find out the average power. How will I find out the average power? So average power will be what? Average power will be, I will integrate this whole graph with respect to time. Torque of f of omega, whatever this value will come out to be, right? This is j alpha, whatever this, I will assume the rate to be alpha to be almost constant. This will, I will assume to be constant, into omega with respect to time, and divide by the whole time period for which I was measuring, right? So let's say it took 10 seconds to totally die down, stop. So I will write here overall time period. So like this you can find out the overall average, although this will not be exactly exact, because there will be some errors, because you see, right, your speed is changing, so your acceleration is also changing. Here your acceleration is almost going to 0, right? So yeah, those things are there, but still I can like I can find out a approximate value. Okay, so this is how you can separate the friction and windage loss. But still I have not discussed how can you separate out the what do you call the this stator copper loss. So how will you separate out the stator copper loss? For that you already know what is the friction and windage loss. You already know what is the you already know what is the rotational losses, right? That is the frictional and windage loss. Now how to identify, how to separate out the iron and copper loss, stator copper loss. So what you will do, you will try to apply different voltages. So first of all you will apply the rated voltage. So what we know is we have two components in the iron loss, hysteresis and eddy current. So hysteresis, right, hysteresis one depends proportional to x, bm proportional to bm raised to power x. So my pH, right, will be basically kh into v raised to power x f into like what is my bm? Bm is proportional to what? Bm is proportional to flux. What is my flux proportional to? Flux is proportional to v by f. Okay, so basically it will be vx raised to power 1 minus x. Okay, then your PE is basically, if it is v square by f square, so f square will get cancelled out, so it will be only solely dependent on v square. So I'm getting two equations. So I will change my voltages and I will plot the data. So in one point I will have this loss, in another voltage I will have this loss, right? In another voltage I will have this loss, and in 0 voltage I will have a loss. In 0 voltage, basically when I'm disconnecting the supply, what will the loss be? It will be the rotational loss. When I'm disconnecting the supply, what losses will be there? It will be the rotational losses. Okay, so this will be the rotational, that is friction and windage loss, also called as the rotational loss. So if no supply is applied, right, it is called as friction and windage or rotational loss. Okay, so this component we have already find it out, right? This is the component that we have already find it out. Now only this much is left, so we'll plot the graph, right? And from here I can, what I can write, I can equate, I can find out the equations. So with numerical methods, with different numerical methods, I can find out this constant. These are all just constant. So what will be the overall loss? Overall wattmeter reading, right? PO. It will be equals to the iron loss, which is a which is basically which is equals to this, right? This two components. So of course x will be, you will be knowing the x, right? You will know what is x. So because you will know the material kh into Vxf of 1 minus x plus Ke, frequency I am not changing, into V square, plus remember you have the stator copper loss, right? If you are changing the voltage constantly, so your currents also will change. You will measure the currents. You will measure the currents 3I, whatever I naught square R, R1. This also will change, right? This also will keep on changing. So you will measure the current. You will put in this equation, okay? Plus the rotational losses is constant, that you have already found out, right? So basically, what things you know? You know this. You know the rotational loss. You know the rotational loss. You know what is I naught, because you will always measure the current. So R1 is unknown to you. This Ke constant is unknown, voltage anyways you are measuring, and this Kh is unknown. All this XF, all these are known. So you have three unknowns constant, right? Ke, Kh, R1. So what you will do? You will have three equations, and you will either use some numerical method to solve those three equations, and from there you will be able to find out this constants, and from there you can again now approximate the value, the loss at any value, right? So from here you can directly find out the iron loss. Okay, so this is how you can find out the iron loss. Trust me, no one in the gate industry has taught this. Okay, no one will even tell you this, but I am telling you this because in future I am expecting a question from this. Till now they have not asked a question something like this, because they know students will not know this much, right? No one in the gate industry has like taught in this much level of details. Okay, so but I am expecting in future they will ask these kind of things. Okay, I hope it is crystal clear now what are the problems. So from here you can easily find out what will be the iron loss. If you are able to find out the constant, next time whenever you know what will be the iron loss, it will be basically the wattmeter reading minus the friction and windage loss. And if you are able to find out this R1 value, then you can directly find out the iron loss by subtracting the stator copper loss. So this is the actual formula for iron loss. Now in the question what they will do, generally they will give you the stator resistance. So there are two things. If R1 not given in the question, then you assume, of course you will assume R1 to be 0. Now if R1 is given, then you will say that my stator copper loss will be 0. Okay, approximately. But if R1 is given, then you will not neglect the stator copper loss, right? You will simply, like, because the current will be given to you, the R1 also is given to you, so now you can simply find out the iron loss, because friction and windage loss also will be given to you. So don't just directly write this, right? So don't directly write. So in this case you can directly say that my Pi will be PO minus the friction and windage loss. And here you can say you cannot say my Pi will be equals to Po minus friction and windage loss, because what will be the problem? The problem will be that I will have a stator copper loss, so you cannot neglect it. You cannot neglect it. Your Pi will be equals to Po minus pre-friction and windage minus 3 I naught square into R1. I've seen many educators, many places, in many places you will see they will just directly write this, right? They will not even try to look into the factor that I naught and R1 are considerable, so your Pi will change. Okay, so just be careful regarding that. So now we will discuss a few things when we are varying the frequency and voltage, what happens to the losses. Okay, no load test, what happens to the no load test when I am varying the voltage and frequency. So if I am operating at rated frequency and if I am reducing the voltage, right, if I am changing the voltage, what will happen? What will happen to the flux? So mainly in no load test we measure the iron loss. So the flux, right, is proportional to V by F. If this is fixed, the frequency is fixed, right, I'm changing the voltage. So if the voltage is changed, it is reduced, so my flux also will be reduced. If flux is reduced, that means what? There will be less magnetizing current. That is sure. Magnetizing current will be less. But what will be the problem? So there will be few problems, we will discuss about those. Okay, because frequency, like synchronous speed will not change, because synchronous speed depends on frequency, right? So F has not changed, so it will depend on frequency, no problem. No load no load frictional loss, right, friction and windage loss, that is the mechanical loss, that also will not change, because it mainly depends, like mainly my motor runs at no load, mainly runs at synchronous speed. So that synchronous speed is not changing, so my no load losses will not also not change, because the no load losses mainly depends on the speed, right? But flux here is reduced. So if flux is reduced, your hysteresis loss is proportional to F raised to power, if you remember, actually it is proportional to Bm. So this will be X, right? This will be X. This will be X. Okay, so it is proportional to X. So of course your coal losses will reduce, because your flux, like your iron losses are proportional to flux, so your coal losses will reduce. So coal losses will reduce, so that is what they are telling. So we are just identifying the effect due to change in the voltage of the no load test. The magnetizing current, again as I have discussed, will reduce because the flux has reduced. Overall no load current will also reduce, right? Hence the stator copper loss will also reduce, right? Everything will reduce. So what is the problem? What is the problem? So wattmeter reading in no load also will show lesser value, because this, right, coal loss has reduced and the stator copper loss also has reduced. Okay, but the power factor will slightly improve. Okay, power factor will slightly improve, but here what is the problem? The problem is in the core rated flux is not getting generated, so I'm not getting the rated core loss, because the motor will not operate in that condition, right? In lower voltage, motor will operate in rated voltage only, so I'm not producing rated flux. So basically I'm not able to measure the rated amount of core loss. So that is the problem here. We are just seeing the effects if we are reducing the voltage, rated voltage, and we are operating in rated frequency. Okay, so what happens is, as the no load component, that is Im magnetizing component reduces, so I know my I naught is what? I naught is the core loss component plus JIM, right? So the imaginary component is reducing, right? So what will happen? So the power factor will basically improve. Power factor will improve because of course imaginary component is reducing. So cos phi is what? Cos phi is basically real IC upon overall I naught current. If imaginary component is reducing, what does that mean? That means the I naught current overall will reduce, but IC is constant. I'm not changing anything with the IC, so it will roughly remain constant. Although it will also change, but it will roughly remain constant. Like this will reduce drastically, so cos phi also will increase. Cos phi will increase. So that's why the power factor will slightly improve. Still, it will be low only, because we are operating in no load. Magnetizing component still will dominate, but power factor will slightly improve. Okay, sorry, power factor will slightly improve. Okay, so that is the case over here. So now if we are operating in rated voltage but less than rated frequency, what will happen? So this time again, what is flux? Flux is again proportional to voltage by frequency. So frequency is now reducing, voltage is constant, so flux will increase. If frequency reduces, the synchronous speed will reduce, right? Synchronous speed reduces. If synchronous speed reduces, that means the rotational losses also will reduce, okay, slightly, because nr is approximately equals to ns, so p rotational losses will reduce, okay. Now if there will be very sharp increase in flux, there will be very sharp increase in flux, because like it is inverse relationship, right? So because flux increases, hysteresis loss and core loss will, sorry, eddy current loss will increase drastically, okay, they will increase drastically, sharply, okay. So so even if frequency is less, increased flux can overcompensate, leading to excessive core loss. The core can get saturated, because more, like for producing the same amount of flux, I have to pass in more amount of current, right? The core can get saturated, okay. So that is the thing over here. Now magnetizing current will increase, because for producing the same amount of flux, the like more amount of flux is getting produced, right? Because flux is getting increased in the core. So if flux is getting increased in the core, who will supply that flux? Only the magnetizing component of current. So magnetizing component of current will increase, okay. Stator copper loss will increase, because it is proportional to I naught square r, that also will increase. So overall wattmeter reading will increase, because even though the mechanical losses reduces, but overall it will increase, because there will be sharp increase in the stator copper loss and core loss, okay. One more thing, the ammeter reading will increase, okay. And the if the ammeter reading increases, one more thing, the magnetizing component of the current will increase, right? If the magnetizing component of the current will increase, what will happen to the power factor? Power factor will worsen. Power factor will worsen. Why? Again, power factor is what? Cos phi. Cos phi is what? Cos phi is IC upon IO. So IO will basically increase, because what is my IO? IO is IC plus JIM. So IM is increasing, as I have told you. Magnetizing current is increasing, so this is increasing. So power factor will reduce. So it is basically worse. It will, like, if it is reducing, it is worsening. Why? Why is it bad? Why power factor reduction is bad? This we will learn in power systems. Okay, don't worry. So it will worsen basically. So this is the summary basically. You can go through this, whatever we discussed. Just you should know what happens if I am changing the frequency and changing the voltage at different levels. What will happen to the no load test? So let's now discuss about the blocked rotor test, also known as the locked rotor. So in this we will be finding out the series parameters. In the previous test we found out the shunt parameters. So in this case what we will do, I have told you, right, we will block the rotor. Rotor will not rotate. If rotor is not rotating, what is my slip? Slip is 1. If slip is 1, then what is fictitious resistance becomes? Slip is 1, so this fictitious resistance becomes 0. So it will be short circuit. Now if it is short circuit, so roughly if I assume that there is very low drop in the stator, so this voltage V is getting applied to this resistance. If I somehow take out this stator resistance on the right hand side, this we can do when we know that the drop here will be smaller, okay. So why the drop will be smaller? Because huge amount of current will flow. Why huge amount of current will flow? Because this resistance has gone, right? Mechanical load is like basically it is we have just blocked the rotor, so huge amount of current will flow. Why huge amount of current will flow? Practically also we can understand, because there is huge amount of flux cut, right? There will be huge amount of flux cut, flux generation. That's why huge amount of current will flow. That will be my blocked rotor test, okay. So here it will be short circuit. So I can neglect this, right, because I have directly like switched my stator resistance to here, directly done that, because the drop will be very smaller. So I can directly do that, because here the current is huge. I2 let's say will be 19.5 amperes, and this time, right, I don't have to apply very high voltage. Why? To pass the rated amount of current. Same reason as the short circuit test in transformers. In transformers we used to give low amount of voltage to pass the rated current, because this resistance, this is what? This is winding resistance and leakage reactance, right? This is just winding resistance and leakage reactance. So these are basically very low amounts. If these are basically very low amounts, so current also will be like basically the volt, like to pass the same, let's say 10 amperes of current, resistance is lower, right? Resistance is 1 ohm. So I just need to pass 10 volts, right? 10 by R will be amp currents. So I just need to pass 10 volts of voltage. So that's why we don't need to provide high voltage. As we don't need to provide high voltage, here the like magnetizing component of current will be very very low, because if I'm providing low voltage, my flux depends on what? Flux depends on V by F. If voltage is very low, magnetizing component of the current will be very low. So IO will be very low. So here whatever currents flow through here is roughly equals to this, right? This current and this current roughly are equal. So basically what I can comment that basically R1 and R2 dash are roughly in series. So that's why I have swapped this place. I have taken out from here R1 and I have swapped it here, R1 plus R2 dash. Okay, so yeah, this is the place, basically this is the case. I hope you have understood this portion. So here where the power loss will happen, so radiated current is flowing, right? Block rotor current, radiated current is flowing. So what is the like, again wattmeter will be connected in the stator side, voltage, voltmeter, ammeter, all those things will be connected. So I can say the power of the block rotor will be what? It will be 3 I2 dash whole square into R1 plus R2 dash. Okay, so this will be the overall copper loss of the winding. From here I can directly, already from the previous test, I will be able to find out the R1, and from here I like, because I know R1, I will be able to find out R2 as well, because I will like, there is a wattmeter, there is an ammeter will measure the current, right? And basically from here I can directly find out R1, I can find out R2 dash. Also one more thing, I have voltmeter, right? If I have voltmeter, what will the voltmeter measure? So voltmeter will measure the voltage divided by current will give me the total impedance is what? R1 plus R2 dash plus J, like basically the magnitude of this, right? J into x1 plus x2 dash. Okay, so that is what my voltage and current will give me. Okay, so these are the things, basically this is what you have understood. So yeah, so from here I have two equations. Basically I will be needing to find out x1 x2, all those things, right? So from here I will be able to find out R1 plus R2, and if I put it here I will be able to find out x1 plus x2. So I just need two equations, right? Because two unknowns, mainly generally we write the winding resistance and reactance together. So that's why I can directly like write this roughly equals to R and this roughly equals to X, right? So I will be able to find out X and R like this. So that is the thing. Also one more thing we can do. So you know the power, right? Power of the block rotor test, PBR, and then if you divide by the voltage into current, right? Voltage into current, voltage of the voltmeter into current. So this is what basically power is what? Vi cos phi. I am dividing by voltage into current. So basically this will be cos phi. Cos phi is like another way to find out the parameters. R by Z, right? R is what? R is basically R1 plus R2. Okay, and Z is this. Okay, so yeah, I hope you have found, like I hope you have understood this thing. So this is what we do. We block the rotor. So basically our rotor will be short circuited. Our rotor will be short circuited. This will be my voltmeter, this will be my ammeter. Okay, so yeah, yeah, from here you can understand like what are the things basically. So what will be R? So for R I can directly write R will be equals to this, sorry, yeah, 3, yeah, this will be equals to PBR divided by 3 into I2 square. Okay, this will be my R equals to. Okay, so this is how you find out the parameters. So here copper losses will dominate here, as the stator and rotor almost carry the same current and full load current. No load current will be negligible. Why? Because the voltage is reduced as flux is proportional to V by F. So flux will be reduced, hence the no load current also will be negligible. So wattmeter reading will be approximately equals to 3 ISC, the short circuit current, into the short circuit resistance. Okay, this is how you can find out. Another way to find out is magnitude of Z is what? Magnitude of Z is R square plus X square. From here you can directly write what is my X. X will be equals to Z square minus R square. Okay, that is what my X is equals to. Okay, so yeah, so I hope you have understood this point. So these are the comparison with respect to transformer. So no load test in transformer measure the core loss and the shunt parameters. Same in case of induction motor, but rotational losses are there plus the stator copper loss. Stator copper losses are there. Okay. In case of short circuit test, we measure the copper loss and the series branch parameters for transformers. For induction motors, we do block rotor, which is similar to short circuit, and we do the same, right? Motor is standstill. We measure the same series parameters and the copper losses, right? Copper losses uh, in the conductors and the windings. So basically here the rotor is standstill, that is motor is standstill. Standstill meaning motor is not rotating, we are holding it. Okay, so like very few questions has came, but whenever they give some question, right, it's a very good question. So let's read this question. Like one question mainly came from the induction motor losses. So let's read this question. The locked rotor current in a three-phase star connected 15 kilowatt 4 pole 230 volt 50 hertz induction motor at rated current conditions is 50 amperes. So it's a locked rotor. Basically we are performing the blocked rotor test. So it is a star connected 15 kilowatt motor. So the rating of the motor is 15 kilowatt. So output, right, the motor output is 15 kilowatt. It's a 4 pole machine. Voltage is 230 volts. And frequency is 50 hertz. Okay, and rated condition, like at rated condition the current is IBR is 50 amperes. Okay, this is the rated current basically, neglecting the losses and the magnetizing current. So they are telling me I will neglect the losses. Losses meaning, so what in block rotor test I will, first of all I will neglect the magnetizing current. So mainly what kind of parameters I have? I have two kind of parameters. One is the shunt parameter, another one is the series parameters, right? R and Jx. So I'm not writing R1 R2, I'm just writing them together. Okay, this is Ri, this is Xi. Now they're telling me neglect the losses. Where can losses happen? In this and this. So here they're telling me to neglect the losses, so I will neglect the resistance because losses can only happen in resistance. Now what next they're telling me? And the magnetizing current. So magnetizing current is due to this magnetizing reactance. So they are also telling me to neglect the magnetizing current. So I will neglect the magnetizing current as well. Okay. The approximate locked rotor line current drawn when the motor is connected to 236 volts and this frequency. So if I am connecting it to 230 volts and 50 hertz, then the current is this. What will be this? What is left? Only this one is left, right? So only equivalent circuit is only Jx. Okay, so here this is the place where I am applying the voltage and this is the current and I am changing the frequency of the voltage as well, right? So what do I know? What does reactance depend? Like reactance depends, it is proportional to frequency. It is basically equals to 2 pi FL. So it is proportional to frequency. So if I change the frequency, reactance will change. Then the current also will change, because what is current? Current in this case, because there is no resistance, current is simply voltage divided by the magnitude of the reactance, right? That is what my current is equals to. Okay, so directly I can say here, is that, so initially what I know, what is the current, what was the current, it was 50 amperes. I know what was the voltage. Remember, this is the line voltage, right, and this is per phase, per phase. So you have to write the phase voltage, right? All whatever we are discussing is per phase. Whenever they mention a voltage, unless and until specified, it will always be line voltage. So this will be 230 divided by, so this I will write here, this is line voltage. Root 3. So this divided by the reactance. Okay. So the reactance equals to 23 by 5 root 3. This is the value of reactance when my frequency is 50. Now my frequency has changed. What will be the new reactance value? New reactance value will be basically old reactance into new frequency 57 by old frequency. So simple like ratio, right? Simple ratio. So this will be 23 by 5 root 3 into 57 by 50. I'm not writing anything for now. I'm not calculating it. I will put everything at the end. Okay. So now next time they are asking me in the new circuit, if the reactance will now become, as the frequency has changed, this has become Jx dash. I'm providing a voltage of 236, right? 236 volts. So this will be 236 divided by root 3. So from here I can directly say the current will be 236 divided by root 3 divided by the x dash. X dash is this value 23 divided by 5 root 3 57 divided by 50. Okay, so this value, this now we will use the calculator. Basically we'll use the calculator. So 50 divided by 23 into 57 into 2 into 250, yeah, 45. This approximately comes out to be 45 ampere. So current answer will be 45 ampere. So these kind of like easy questions will come, mostly easy questions only will come, but if you don't know the concept, exact concept, you will mess up in the examination. So just be careful regarding the concepts. Okay, so 45 amperes will be the answer for this question. And yeah, that's it basically for this lecture. In the next lecture we will discuss about starting of induction motor, different methods of starting of induction motor. Thank you and happy learning.